So in the satellite navigation principle, we need to measure the distances to the satellite from our observation locations or from the receivers. For this purpose, we carry out two types of measurement. The first one is the pseudo-range measurements, and the second one is the phase measurements. So the pseudo-range measurements are coarser than the phase measurements. So the phase measurements are more precise than the pseudo-ranges because the electronic systems available in today's technology can measure 100th of the signal's wavelength. So, for example, for coarse acquisition code of GPS, which has the 300 meter wavelength, so the receiver can measure 100th. So this means 3 meters, okay, accuracy. The distance between the satellite and the receiver can be measured by 3 meters. Whereas on the other hand, the phase measurements can be done with higher accuracy. So the carrier phase or the carrier frequency of the GPS signer, for example, is 19 centimeters or nearly 20 centimeters. So if you divide 100th of the 20 centimeter, you arrive at a resolution or the accuracy around 2 millimeters. So that's the reason why phase measurements are more important than the pseudo-range measurements for geodetic positioning. So for both of the measurements, so we need to make a model. We need to express our measurements within a model. So at the left-hand side, you see the measurements carried out by the receivers. So the pseudo-range measurements, and the capital phi denotes here the phase measurements. These are both scaled. So normally phase measurements are not made in the meter units, but they are scaled by using the velocity of light. So that's why these two measurements are scaled, so in meter units. So as you can see, the left-hand side includes the measurement itself. So for example, in pseudo-range measurement, and the right-hand side includes the parameters of my model. So as you can see here, so the first term denotes the geometric distance, which means that if I have perfect clocks at both ends, the receiver and the satellite, I would obtain the direct distance in a vacuum. So for example, if there are no hindrances like the atmosphere, for example, we will see ionosphere or troposphere. If I had perfect measurements, if I carried out perfect measurements, I would obtain the direct the geometrical distance between the satellite and the receiver, and this is the geometric distance. But as said previously, the satellites are not perfect. That's why I get a receiver clock error and the satellite clock error at both ends. So in addition to those errors, there are some other errors you can see here. These are, for example, hardware delay at the receiver and the and the satellite's hardware delay. So this is for the receiver, the first term, and the second term is for the satellite. And the signals travel through the atmosphere, and the two important layers of the atmosphere, two important layers for the atmosphere should be taken into account for the measurement model. So in pseudo-range measurements, for example, as you can see, this sign is plus, and you will see later in the phase measurement, this sign will be negative. And this error is called as the ionosphere error. So the distances will be larger due to the ionosphere. So that's why we call this error as the ionospheric delay. And in the lower atmosphere, where the rains take place, for example, or the weather events take place, so we call this troposphere, and the troposphere makes also some disturbances to the satellites. This also causes delays in the travel, so that's why we should also take into account the tropospheric error. And another error term is the multipath. So in open sky or in an environment where nothing is available, even a tree or on bare land, on a flat land, so if your receiver will obtain the signals without any diffractions or without any the signals will come directly to the receivers in and at that flatland locations. But in cities, for example, in city canyons, the signals will not come directly to the receiver, so they will be reflected back from the, for example, the buildings or especially metallic surfaces. Then you will obtain not the direct line of sight, so not the distance between the satellite and the receiver, but the distance will then get increased. So this error will be called as the multipath error. Multipath error. And the last term is the statistical term, which is the random one. So as you know, so we try to model first the systematic errors. So these can be called as systematic errors. So the multipath can also be treated as systematic, but it is difficult to model. That's why we leave this error term to a side. But if we have exhausted the terms, all the model terms are already used, then we still have the measurement error. So due to the imperfections of the receiver, for example. So that's why we introduce random errors here by using V. And the same equation is also available here in the phase measurement, but there are two differences between the pseudo-range measurement. So the as you can see, there is also an index denoted by phi, lowercase phi, so which is the indication for the phase measurement, phase measurement here, and the satellite, receiver clock phase measurement, satellite clock phase measurement, and receiver clock hardware delay, satellite clock hardware delay, etc. And the first difference here is, as you can see, this the ionosphere term is included as minus sign, not positive here. This is positive here, it is positive, but here the sign is negative. And that's why the phase measurements are not delayed, that they are advanced. So one main difference is in the ionosphere term. As you can see, troposphere and the multipath terms does not change. So for code measurements and for phase measurements, the multipaths, amount of multipaths are different. But we don't want to go into the details of that issue in the scope of this lecture. The very important other one is, again, you see here the term here. So as we noted earlier, at the turning on of our receiver, we don't know the exact full number of full cycles. So, and at the very beginning of this process, of the measurement process, we cannot know the full number of full cycles. That's why we call this as unknown. We must model this, and this unknown is called as ambiguity, okay, or integer ambiguity, and its resolution is important for phase measurement. So we have introduced a ruler example. So as you can see in the code measurements, you have no phase integer ambiguity term. You can see in the entire term there is no ambiguity term, but here we have ambiguity. So because the phase measurements are depicted as the rulers having no units. So this is the reason why that example is introduced. So in order to make our phase measurements efficient for the geodetic positioning, we need to also estimate the number of full cycles at the beginning of at the turning on time of the receivers. So the pseudo range measurements and phase measurements are modeled in this way. In the later example, we will under some assumptions try to model the pseudo range and phase measurements on an example, on a concrete example. So at the beginning of this lecture, we introduced this graph, and we would like to make some amendments to this graph. So as you recall, the satellites, each GNSS satellite produces 3 layers, and these 3 layers are modulated into one unique signal, and this signal will be sent to the receivers on the Earth or also to the space vehicles in space anyway. So, and these signals will be obtained by the antennas will capture the signals, and then the receivers later will process further. And the duty of the receivers is to get the information. So for example, the satellite position information. The other one, the code observations, and the other one is the phase measurements or phase observations. So these 3 layers are demodulated again by the receiver. So the receiver, each receiver has its own data structure, and so this means that from receiver vendor A to receiver vendor B, for example, the registration of the signals is different. So let's take, for example, the Leica company. So it uses a registration strategy different from the registration strategy of, let's say, Trimble. So that's why the receiver type is here important, and each receiver stores the signals in its own data structure, whose inner structure we don't know. So this is called as a binary format. So this is binary, means zeros and ones. So as you know from the principles of electronics, so it functions in this way. So the signal passes or doesn't pass, for example, 0, 1. And this is the binary format, but we must convert these signals, the necessary signals. So for example, the first is the satellite positions are stored in a navigation data file, and the observation, so code and phase observations are stored at another file. For this purpose, we use 2 types of files which are readable by the users. So compared to the binary files, so the binary files cannot be read directly by the users. That's why the the hardware producers will generate human readable files, which are called as RINEX files, receiver independent exchange files. And there are three types of RINEX files. The first one is the navigation message file, where the satellite data, so in terms of Keplerian parameters or their time elements, so timely changing elements. And the other file would be the observation file, where the code and phase observations are stored. So there are some other options, for example, Doppler and signal to noise ratio can also be stored. But so we concentrate on code and phase here. And the third one of the RINEX file is the meteorological one. So we will not deal within this lecture, but so please at least have heard that the name of the RINEX file in meteorological, for example, is meteorological file. So now in the next lecture, we would like to give the the structure of the navigation and the observation data files. So and the reading or make computers read those files is necessary in order to make some computations or to carry out some computations for determining the positions of the receiver locations.